Alright, so I want to take a little bit and look at the book here and how we can talk about standard deviation. So notice each of these samples has a mean of 5. This has a standard deviation of 0. All of the data entries are within bin 5. So there's no spread. This standard deviation is 1.2. And what we'll see is that means that there's a certain amount of data, 68% to be exact, on either side of the mean, a distance of 1.2. So if I go up to 6.2 and down to 3.8, I get most of my data. And here, this has a standard deviation of 3, and so most of the data is between 8 and 2. There's little bits that aren't, but most of it's there. And so that's what the standard deviation does for us, is it tells us where our data is. So let's look a little bit deeper. I'm going to skip down to a graph here in the notes and use this graph. And this is called the empirical rule. And it talks about, and this is the same for a population or a sample. They're using the sample here just to show. And if I have all of my data, we can see is this hump. And we'll study this hump more in what we're going to call a normal curve. And so this is data that's symmetric and bell-shaped. Within one standard deviation on either side is 68% of the data. 34% in the positive direction and 34% in the negative direction. Within two standard deviations, right, in both directions, is 95% of the data. And then within 3 standard deviations is 99.7. And so most of your data is within 1 standard deviation of your mean. And this talks about how far away from the mean your pieces of data are. And so we can talk about data in its distance from the mean. And we're in the next section, we're going to find a way of making a standard measure that measures things in standard deviations. We're going to call it the z-scores. But for right now, if we know certain values, we can figure out what their percentages are. So I'm actually going to look at the example in the textbook. And it says, in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States aged 20 to 29 is 64.2 inches, with a sample standard deviation of 2.9 inches. Estimate the percent of women whose height are between 58.4 and 64.2. Alright, so if the mean height is 64.2 and the standard deviation is 2.9, what we want to do is we want to look at where we are in here. So I'm going to switch over to my drawing pad here. And I'm going to scroll past this here. Give me a second. So we have a mean of 64.2 and a standard deviation of 2.9. And so it's asking us, again I'll flip back to it, of how many people are between 58.4 and 64.2. So we're going backwards. Now right now we know from the empirical rule that 34% is here. Right, now I'm going to go to that chart here so you can see it. 34% is here, and 13.5% is here. And then in 2.35 in the little tail here. So if we come back, let me switching things around here. So we want to figure out how many standard deviations back we are. Well, if I count backwards, so if I take 64.2 minus 2.9, that's going to give me this boundary here, which is 61.3. And I take 61.3 minus 2.9, that gives me 58.4. And so what it's telling me is, if I think of my bell curve here, and that's my mean, and that's my 1 standard deviation, and that's my 2 standard deviation, and that's my 3. 58.4 is the second standard deviation to the mean. And this was 34%, and this other one was 13.5%. So the percentage of things in between there would be 34% plus 13.5, or 47.5%. And so this is telling us in between these regions, there's this. And the textbook even goes in a little deeper. It says that, realistically, this is actually 34.13%, and this 13.5 is 13.59. Adding up again in chapter, or in section 5, we'll find a way of getting these numbers a lot more detail to them. And in chapter 5, we'll put in big details to these altogether. And so this is called the empirical rule. And it helps us tell how much stuff we have in between known boundaries. And those known boundaries are how many standard deviations away we are from the mean. Related to, I lost my place here. Related to the empirical rule is Chebychev's theorem. Now, notice when I said in the empirical rule that we want these things to be bell-shaped and symmetrical. And so there's as much stuff on this side of the mean as there is on this side of the mean. And so these gives us what is called the bell curve, and however much stuff is here is over here. Well, for other distributions, we have Chebychev's theorem. What Chebychev does is he says, well, we don't get this nice symmetry. I can't calculate exactly what it is, but I can estimate it. But I'm not going to be able to estimate it greatly. I can do for greater than 1 standard deviation, so I can do 2 standard deviations. What I can say is I can spit out a fraction. If I want to know how much is within 2 standard deviations, it's going to be 1 minus 1 over 2 squared, which is 3/4 or 75%. Well, I know how many is in 3 standard deviations. It's 1 minus 1 over 3 squared, which is 8/9 or 88.9%. And so Chebychev's theorem says, well, we can look if the stuff isn't symmetrical, it's uneven and spread out, we still have a standard deviation of its spread, and we can estimate how much stuff is within 2 standard deviations, which would be 75% of the stuff. And so Chebychev's it gives us a way of calculating how much stuff would be within in a range. And Chebychev's is, I think, the hardest part. Let me go back one screen here before I go into this in detail. Is that it's an approximation. It's at least how much stuff is there. It's not as detailed as the empirical rule for exactly how much stuff is there. All right, I want to stop these for the approximation data, and then we're going to look at the standard deviations for data that's grouped together using frequency distributions and ways we can estimate those. And that will end section 4.